Welcome to Energy Quantization. So let's take a look at the major developments that led us to the conclusion that energy is quantized and not continuous. Now, the classical mechanics approach to the description of blackbody radiation, which is shown here in this graph, results in the ultraviolet catastrophe. That is, the classical theory matches what we see, so we see these curves, the red, green, and blue curves, for an actual blackbody radiation. But the classical theory predicts this black curve, which matches the observed results reasonably well at low frequencies, that is, long wavelengths, but it fails spectacularly at shorter wavelengths, higher frequencies. This is farther to the left on this graph. Now, a hot object emits electromagnetic radiation, that is, it glows. So if you heat up something like a fork, it will eventually begin to glow, first red, and then yellow, and then eventually white, as the temperature of that fork increases. Now, all objects will do this depending upon their temperature. So as the temperature increases, then a greater proportion of the emitted light is short wavelength light, so high frequency light. This is going to tend closer to the blue side of the spectrum as opposed to the red side of the spectrum. So again, as the temperature increases, the object glows first red, then orange, then yellow, then white, and eventually, if you get it hot enough, it will glow blue. Now, the energy density, which we're going to symbolize with this scripty E here, so the dE is the total energy in a region of the electromagnetic field divided by the volume of that region. And this will have units of joules per cubic meter. So this 3 here should be superscripted. And so that energy density dE is going to be equal to rho, where rho is this density of states of our system, times d lambda. And rho here is just this constant of proportionality between our energy density and our wavelength region that we're looking at. Now, the total energy density in some region, which is now E, which again is a function of temperature, the total energy density in a region is going to be equal to the integral over all of our wavelengths, right? So now we're integrating over our wavelength region. And then the higher the temperature, then the higher the energy density. Now, the total energy within a region is the energy density multiplied by the volume of that region. So we've got here our energy density, and this is, note, a script dE, whereas on the other side of the equation over here, we've got a non-script dE. So on the left side, we've got the total energy within that region, and that's going to be equal to the energy density, the script dE, times the volume of our region, V. Now, the Rayleigh-Jeans law predicts the density of states. So we've got our density of states, rho, is equal to 8 pi k times the temperature divided by the fourth power of the wavelength. Now that k there is the Boltzmann constant, which is 1.381 times 10 to the minus 23 joules per Kelvin. Now, while the Rayleigh-Jeans law matches the experimental observations fairly well at low frequencies down here and high wavelengths, it fails to accurately predict the experimental observations at high frequencies and low wavelengths up here. Now, the total energy density in a region is predicted by the Rayleigh-Jeans law to be infinite, that is, this goes up to infinity, at all temperatures above absolute zero. Now, this is an absurd result, and this is what we call the ultraviolet catastrophe. That is, the Rayleigh-Jeans law doesn't work in the ultraviolet region. As the wavelength gets lower, as the frequency gets higher, the Rayleigh-Jeans law suffers this catastrophic failure to predict the physical result. Now, in 1900, Max Planck finds that he can account for the experimental observations by proposing that the energy of each electromagnetic oscillator is limited to discrete values and cannot be varied arbitrarily. That is, that these electromagnetic oscillators are not allowed to have a continuous spectrum of values, energy values. They're only allowed to have certain values. And this is where the idea of quantization of energy comes from. Now, the emitted energy at frequency nu must be an integer multiple of the energy of h nu. This is the energy of each photon. So that means that the total energy emitted at some frequency has to be n, some integer multiple of h nu, the energy of the photon. That is, if we have, say, 5 photons, then n is 5, and the total energy emitted at that frequency must be 5 times the energy of a photon emitted at that frequency. And note here that h then is Planck's constant, the 6.626 times 10 to the minus 34 joule seconds. And again, this minus 34 should be superscripted. Now, using this assumption, Planck was able to derive the Planck distribution, which looks like this equation here. 8 pi times h, Planck's constant, times c, the speed of light, divided by the 5th power of the wavelength that you're examining, times the quantity e to the hc over lambda kt minus 1. So again, we have that Planck distribution up at the top of the screen here. Now at high frequencies, these are small values of lambda, then this fraction here, hc over lambda kt, is much greater than 1 because lambda is small and that makes the value of that fraction very high. And that means that our exponential term here approaches infinity faster than the 5th power of the wavelength goes to 0. And that means that the energy density approaches 0 as the wavelength approaches 0, or as the frequency approaches infinity. And this then agrees with the experimental observation. So if you remember that graph, we had a graph that looks something like this, right? Where we're talking about here on this side, the energy density goes back down to 0 on the left side of that graph. Now, at low frequencies, these are large values of lambda, so this is the right side of that graph, then the value of this fraction, if lambda is large, then the value of this fraction is much smaller than 1, and that means that the denominator here in our Planck distribution can be replaced with what we have at the bottom of the screen here. That is, this term in parentheses, so this term, can be replaced with this side over here. So let's take a short math aside. The series expansion of an exponential function, so if we have an exponential function e to the x, we can expand that into 1 plus x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x squared, x cubed, and so on. So that is the sum from n equals 0 up to infinity of x to the nth power divided by n factorial. Now, if x is much less than 1, then each subsequent term here in our series is going to be much smaller than the previous term. So that is, x squared is going to be much smaller than x. And that means that we can basically ignore every term past these first two, where we have 1 and x. And that means that a decent approximation is that e to the x is equal to 1 plus x. Now, if we use that approximation in the Planck distribution, we then get the Rayleigh-Jeans law. That is, the density of states here, we know, is equal to this 8 pi hc over the 5th power of the wavelength times this term in parentheses. Now remember that this term in parentheses, we can replace this e to the hc over lambda kt with 1 plus hc over lambda kt. Well, now we're subtracting 1, so we're just left with hc over lambda kt. And now we have some algebraic rearrangement. We've got hc cancels with hc here, kt here moves up to the numerator, and our 5th power here cancels and goes to the 4th power. So we end up with this term over there. Now, the total energy density is no longer infinite. Instead, we now have the total energy density E as a function of temperature is now equal to the integral of this term, and that's then going to equal A times T to the 4th power, where A is this fraction down here. And this means that now the energy density over here, that's script E, is going to increase as the fourth power of the temperature. Now in the early 1800s, Pierre-Louis Dulong and Alexis-Therese Petit determined the heat capacities of a number of monatomic solids. That is, the constant volume heat capacity, C sub V, is equal to the partial derivative of the internal energy, U, as we change the temperature, keeping the volume constant. Now, they proposed that the heat capacities of all monoatomic solids are the same, and those values are close to 25 joules per mole Kelvin. Now, if classical physics were valid for atoms, then the equipartition principle could be used to infer that the mean energy of an atom as it oscillates about its mean position is kT for each direction of displacement. Now, each atom can then oscillate in 3 dimensions, so the average energy of each atom is going to be 3 kT. And then for n atoms, the total energy is then 3 n kT. So now if we extrapolate this to a mole, then the contribution to the molar internal energy is, so the molar internal energy here is 3 times Na, where Na is Avogadro's number, times kT. And that then equals 3R, because Na times K is equal to R, the gas constant. Now that means that if we're looking at the molar constant volume heat capacity, so now we've got a V and an M subscripted down here, that's then going to be equal to the partial derivative of the molar internal energy with respect to temperature as we keep volume constant, and that's going to be equal to 3R. Well, the value of 3R is 24.9 joules per mole K. Now, unfortunately, as advances in refrigeration made it possible to measure heat capacities at low temperatures, it was found that molar heat capacities of all monatomic solids are lower than 3R at low temperatures, and the values approach 0 as the temperature approaches 0. Now, in 1905, Einstein assumed that each atom oscillated about its equilibrium position with a single frequency. He also used Planck's hypothesis to assert that the energy of oscillation is confined to discrete values. And this led him then to the Einstein formula, which gives him the constant volume molar heat capacity is equal to 3R times this Fe, where that Fe is shown over here, to be equal to this lambda E. Now lambda E here is the Einstein temperature. Now this is Einstein's way of expressing the frequency of oscillation of the atoms as a temperature, where a high frequency corresponds to a high Einstein temperature. So this scripty F sub E term is equal to the Einstein temperature divided by the actual temperature of the system squared times E to the Einstein temperature divided by 2 times the temperature divided by the E to the Einstein temperature divided by the temperature minus 1, and all that big quantity squared. And note here that the Einstein temperature, this lambda E, is equal to h nu over k, where h is Planck's constant, nu is the frequency, and k is the Boltzmann constant. Now, at high temperatures then, the actual temperature of the system T is much larger than the Einstein temperature, lambda, and that means that we can simplify our expression here, and it ends up simplifying to 1, which means that in this equation down here at the bottom, then if the value of F is 1, then our constant volume molar heat capacity is equal to 3R, which matches the classical result that we had seen earlier. Now, at lower temperatures where the classical result failed, this is now where the temperature is lower than the Einstein temperature, and in this case, now our value of F does not simplify to 1, but we can approximate it here as this value over here on the right side. Now, the exponential function, that's this term here, goes to 0 more rapidly than 1 over t goes to infinity, and that means that our function here approaches 0 as the temperature approaches 0, and that means that the heat capacity also approaches 0 as the temperature approaches 0. Now, the physical reason for this decrease in heat capacity is that at lower temperatures, only a few of the oscillators possess enough energy to oscillate significantly, and thus the solid behaves as though it contains far fewer atoms than it actually does. And at higher temperature, there is enough energy available for all of the oscillators to become active, and then all 3n oscillators contribute to the heat capacity, and that means the heat capacity approaches our classical value of 3R. Now, in practice, the Einstein formula predicts the shape of the heat capacity versus temperature curve, but it still fails to accurately predict the experimental results. So the Einstein formula fails due to the assumption that all of the atoms oscillate with the same frequency, whereas in reality they oscillate over a range of frequencies up to a maximum value nu d. And this then leads us to the Debye formula, which is similar to the Einstein formula, and again, it has this theta d term, so instead of theta E with the Einstein temperature, theta d is the Debye temperature. Now, the Debye formula successfully predicts the experimental observations of the heat capacity at all temperatures. So now let's turn and look at atomic and molecular spectra. Now, the atomic spectra show that radiation is emitted or absorbed only at discrete frequencies. So we've got three different spectra here. We've got the spectrum for hydrogen, where you can see 4 lines in the visible. We've got the spectrum for mercury, and we've got the spectrum for neon. So if we look at the hydrogen spectrum, we've got these 4 lines, and note that as we move from left to right, the lines are getting spaced out farther and farther. Now, the only way that we can explain these spectra is if the energy of an atom is limited to discrete energy values. And so on the right here, you can see we have our energy values, our energy levels, 1, 2, 3, 4, 5, 6, and so on up to infinity. And note that they each get closer and closer together as the value of n gets larger. And so for hydrogen, then, the 4 emission lines that we were seeing were these lines here, because the larger energy values down here from series 1, those occur in the ultraviolet range, and our eyes can't see them. The smaller energy values occur in the infrared region, and again, our eyes can't see them. So those values, those emission lines that you're seeing there, correspond to these transitions, A, B, C, D. Now, note that the line all the way to the left on that previous slide, that in the violet range, that was actually this D value here, where we have an electron transitioning from the 6th energy level down to the 2nd energy level. And the one next to that was from the 5th energy level down to the 2nd. The one next to that was from the 4th down to the 2nd. And then that red one, the one all the way on the right in the hydrogen spectrum, was this value going from the 3rd energy level down to the 2nd energy level. So to sum up, the major developments that led us to the conclusion that energy is quantized and not continuous was first, the Blackbody radiation and the Ultraviolet Catastrophe can only be explained if energy is quantized. The second one was heat capacities. Our observations of heat capacities at low temperatures could only be explained if the energy of the oscillators, those atoms, are quantized. And third, the atomic and molecular spectra that we see can only be explained if energy is quantized. And that was energy quantization.